Hello everyone, welcome to Deeksha Karnataka YouTube channel, and today in Masterstroke series I am going to discuss a very important chapter, which is alternating current, also known as AC. Right now, alternating current is important if you are preparing for your PUC exam. One definite numerical problem is going to come from this chapter. Also for KCET you can expect 3 to 4 questions from this chapter alone. So if you have not yet studied this chapter, or if you want to revise it chapter, definitely this video is going to be very helpful. Here we will discuss in detail about all the concepts. So don't go anywhere, watch till the end, and obviously if you still have any doubts after you watch this lecture, don't forget to mention that in the comment section below. And also I request you, if you have not joined our WhatsApp channel, don't forget to join the WhatsApp channel. The PDFs will be shared in our WhatsApp channel exclusively. Also this lecture notes and all the lecture notes that we have done in Masterstroke series and all the other series will be exclusively shared in our WhatsApp channel only. Also, if you have not yet subscribed, then don't wait, subscribe now. So let's start with all the topics that we are going to discuss today. So DC and AC basic difference, AC applied to resistors, phasors, AC applied to inductors, AC applied to capacitors, and obviously LCR series circuit. I think they are missed, LCR series, and obviously the resonance. So these are the things that we are going to discuss today. Right, now let's start. DC and AC. So DC also called direct current. Okay, direct current means the current's direction does not change with time. Okay, so current's direction that does not change with time is called direct current. Okay, generally any direct current is represented a graph like this. Suppose this is a time, this is the magnitude of current. So ideal DC current should be like this. Ideal current means it should be constant. In practical cases, even if it is like this, this is also called a direct current because it is not going in the negative side. So this is the positive I, current positive I, this is negative I. So if it is always positive, then we call it a DC current. Similarly, if the current is always negative, then also it is called a DC current. Right? AC or alternating current, the current that changes its direction with the time. So for example, we have shown 3 different diagrams for AC. Each of them are AC wave. Okay, so here is a rectangular wave or square wave. So here you can see the current is positive in the first half, suddenly it becomes negative in the second half. This type of current is an AC. Here it is called a triangle wave. Triangular wave also, it is again increasing, then decreasing, going to negative, and then again coming back. So these two are also under AC, as well as our very common sine wave. Okay, sine wave, this is not only AC, these 3 are also AC. If everything is above the positive axis, then that will be a DC. Suppose instead of having this, if we have this, then 0, then this, so this kind of graph is also DC. Okay, DC can be anything. If everything is positive always, then they are considered to be DC, no matter if there is a fluctuation. Okay, then it is called a ripple factor. Ripple factor can be determined, it can be eliminated as well using various filters. But if the direction is being changed, then only one way to rectify it. We will study about rectifiers in semiconductor chapter. AC varies as sine function. Normal AC for this chapter, whatever AC current we will take, that will be a sine function. V equals to Vm sine omega t. So this is the general form of AC that we will study in this particular chapter, but for all of your convenience, you should know this kind of graphs are also considered AC. It was very common in exam that they will give you 4 different diagrams, and they will say which of them is AC or which of them is not AC. So you have to identify if it is positive and negative both, then it will be AC. If it is only positive, even though there is a variation, even if it is only positive or only negative, then that will be a DC current. Clear this fundamental concept? Now let's move on to the next part. So voltage function, that as we have seen in this chapter, we will be using voltage function V equals to Vm sine omega t. Current function corresponding, so if there is a current in an AC circuit, so if you apply voltage, then there will be a current also, right? The current function normally is represented using the formula I equals to Im sine omega t. Here Vm and Im is called the maximum voltage and maximum current. So this is the magnitude or amplitude of voltage or maximum current. That's why Vm means V max. Im represents I max. Okay, now in AC circuit something complicated happens. That's why this sine omega t, even if you apply sine omega t, the current can be sine omega t plus phi. We will explain that in detail in a short while. The time period means when there is an AC, it repeats its motion, right? For example, if you consider this, so this is a one single time period. The time required for the AC to complete one complete oscillation is called time period of AC, which is very, very important. And frequency of AC is F equals to omega by 2 pi or 1 by time period. And omega is the angular frequency or angular velocity. Generally this is normal frequency. This is called angular frequency. Now angular frequency and angular velocity are same. Okay, angular frequency and angular velocity are same. That is a common term used in rotational motion. So AC has a very common link with rotational motion. Then also that also we will explain. But these terms are very, very important to remember for you. Now AC voltage applied to resistor. So far in the chapter DC, we have whatever we have studied are actually based on DC. The current electricity chapter entirely based on DC current, and there we have studied everything only through a resistor. Current is being passed through a resistor, series combination of resistor, parallel combination of resistor. Okay, so first thing that we will start in the AC chapter is also using a resistor. Okay, so here is the AC source. The symbol for AC source is given like this. Symbol for DC source, yes, this one is symbol for DC source. This is the battery or cell. Okay, so battery or cell, this is a DC source, this is an AC source. Okay, AC is varying with time, so that's why there is a wave sign over here. Okay, so this is basically a AC battery. You can say this is like an AC battery. Okay, now when you apply voltage, AC voltage across a resistance, will the Ohm's law be valid? Yes, Ohm's law will be very much valid, and from Ohm's law we know V is equal to IR, and from there you can even calculate the current, and the current turns out to be Im sine omega t. So in this case the phase difference phi is exactly 0. Okay, so the current and voltage are in same phase. So for a pure resistor, current and voltage are in the same phase. We will explain phase. Im is called Vm by R. So Im is the maximum current. It is same as our DC case. Only for maximum current we can use this formula to calculate the maximum. From maximum voltage we can calculate the maximum current. Okay, now what is the power dissipated? Power dissipated is P is equal to I square R. Okay, and from there we can say that average power dissipated is half I square R. Okay, so in AC circuit, average power dissipated is actually half of that it was dissipated in a DC circuit. So power dissipation is less. Now AC voltage now to express AC power in the same form as DC power, that is I square R, a special value of current is defined and used. It is called root mean square or RMS or effective current, and is denoted by IRMS or capital I. Normally AC currents are denoted by small I. Okay, you may follow it strictly at this level. It is not very essential, but at higher level, as you move to your engineering classes or maybe in your physics classes, when you move up, okay, then AC current will always be represented by small I. So if you see small I as a current, that will be AC current. Capital I current is basically represented by DC current or RMS current. Okay, so IRMS is the DC equivalent of AC current, and that is given by Im divided by √2, and similarly VRMS is given by Vm by √2. So maximum value of current, when you divide it by √2, you get IRMS. Similarly, if IRMS or VRMS is given, okay, then you have to, so suppose you are trying to find the maximum voltage from Vrms, then it will be Vrms √2. Okay, this is also sometimes be very, very handy. Okay, so IRMS and Im are related through this relation. Now let's see one question. The frequency of an alternating current is 50 Hz. What is the minimum time taken by current to reach its peak value from RMS value? Very, very interesting question. The frequency is given 50 Hz. So 50 Hz is the frequency. So time period is 1/50 seconds. Okay, so complete one oscillation, it takes 1/50 seconds. What is the minimum time taken by current to reach its peak value from RMS value? So it is not from 0. If it is starting from 0, 1/4 would have been the answer. 1/4 of this time period would have been the answer. Okay, so if you see that from starting from 0, okay, this is the graph. So this is this entire time is t. So this must be t/4. This is also t/4. These all are, these small junctions are all t/4. So add all of them, you will get total time, that is t. Okay, so starting from 0, t equals to 0. Okay, how much time it will take? It will take a time of t/4. Now we have to find starting from RMS value. You have to start at RMS value. So we know that current is given by Im sine omega t. Okay, and as I mentioned, if you start from t equals to 0, at t equals to t/4, you would have get the maximum value. So maximum value, we know that t equals to t/4, that is 1/200. 4 5s are 20. So 1/200 seconds, starting from 0, you would have reached its max, but RMS value is somewhere here. This is the IRMS. Okay, now if you don't know the time for IRMS, right? So you have to find this time difference. So the question is basically asking you to find this time difference. How to do that? For that we have to use our equation I is equal to Im sin omega t, and from here at I equals to IRMS, that should be Im by √2. Right? So for this we have to find the time t, which is say tr. Okay, I am just mentioning tr. So Im by √2. So we have to satisfy this equation. Im sin omega tr. Okay, so Im cancels. We get sin omega tr equals to 1/√2. So what is 1/√2? 1/√2 is sin pi/4. Okay, sin pi/4. Right, 45 degrees. So from here we say that omega tr equals to pi/4, right? So this angle must be equals to this angle, or tr equals to pi by 4 omega. Now what is omega? Omega is given by 2 pi f. Omega equals to 2 pi f. Frequency is given here 50. So we have to put that value, pi divided by 4 into 2 pi into f. Okay, pi cancels, and we get this time as 1/4 into 50 into 2. So that is 400, 1/400. Okay, so it will be 1/400. So what is the time difference? Time difference is TR and T. So T minus TR, that is the time difference, minimum time taken, 1 by 200 minus 1 by 400, and if you subtract them you will get 1 by 400. So that is multiply 5 in top and bottom, sorry, not 5, 2.5. okay, so 2.5 into 10 to the power of minus 3 seconds. Okay, 2.5 into 10 to the power of minus 3 seconds. So now these calculations you have to learn how to do it. Okay, so if you see 4 times 2.5 is 10. So that's why we have done 2.5 top and bottom. 2.5 top and bottom. 4 into 2.5 is 10, so 10 and 2 more zeros, so 2 more zeros means it will be 10 to the power of minus 3. So 2.5 into 10 to the power of minus 3 seconds, it will reach from its RMS value to its peak value. Okay, now this calculation again can be shortened if you do it little faster. Okay, I have written the equation, I have written this condition. You should directly start from this equation, then you can save some time. And if you put the omega value directly to pi f in this equation, also you can save some time. This is very common type of KCET question. Now phasors, very important part. Phasors, some of you may have studied in the chapter waves and oscillations, but in AC chapter this is the major concept. In order to show phase relationship between voltage and current and AC circuit, we use the notion or the use a specific design notion of phasors. Phasor is a specific concept that we will be using to determine what is the phase difference between current and voltage. Current and voltage are not always in the same phase. They actually change their phase based on the condition. Okay. A phasor is a vector which rotates about the origin with the angular speed omega. So angular speed omega is there, V is equal to Vm sin omega t. Ideally V is equal to Vm sin omega t is a equation of simple harmonic motion, right? Simple harmonic oscillations can be represented by that. Now simple harmonic motion, we have studied that simple harmonic motion can be related to a circular motion as well. So if you take the projection of a circular motion, on a straight line, you get a simple harmonic motion, right? So when the object is here, you get the this is here, so it rotates over here, you get the object over here. Now object comes back over here, you get a projection over here. So when the object is rotating in this circle, you are seeing that the object is rotating along this straight line. So projection of a circle in a straight line is basically giving you a simple harmonic motion. So circular motion are actually a simple harmonic motion. Okay, now using the same concept we can use in case of AC as well. So AC, what we assume? We assume a simple vector which is rotating in a circle. A vector rotating in a circle, this is called phasor. This is called phasor. Now phasor, the phase changes with time obviously because the angle it makes with the axis is omega t. Angle it makes with the axis is omega t. So at any time, whatever the angle it will make, that will give you the position, current position. Based on time, as you are progressing along the axis, you will get the omega t vector, and that will point towards the direction of that corresponding vector. So for example, in case of resistors only, the current and voltage, so if current is voltage is this, then current is given by this value. Slightly less obviously, right? Because at peak value we know that Im is equal to Vm by R. So it is slightly less. So if Vm is say 10 volt, resistance is 2 ohm, then Im will be 5 ampere. So units will be different obviously, but if you plot them, you will get this kind of graph. Now this graph goes till infinity. Time can go up to infinity, right? So it is very much impossible for us to draw this kind of graph. So what we do, we take the projection of this motion into a circular motion like this, and we represent them using these vectors, and that is called phasors. Phasors is a vector which actually presents the current situation of the current and voltage. okay, and no matter how many times you rotate them, the corresponding graph will continue to produce. But if we ignore this graph, only this graph is sufficient for us to study any AC related cases. That's why this is very, very important, especially for cases like voltage applied to inductor and voltage applied to capacitor. First we will study with voltage applied to inductor. Inductor means, if you have followed my lecture, you should know inductor is basically a coil, okay. When a current is being forced through a coil, the coil tries to resist the flow of charges, or tries to resist the current that is being passed through it. For normal DC, that saturates after initial few seconds, but for AC, where current is changing every second, inductor tries to stop that current every second as well. So inductor behaves like a resistor in AC circuit, okay. Inductor behaves like a resistor in an AC circuit, and that is called inductance or inductive reactance, okay. Reaction, it is giving a reaction to the change in current, okay. That's why it is called inductive reactance, or sometimes simply inductance. The current through an inductor is given by I equals to minus Vm by XL omega t. So there is a negative sign coming, okay. There the derivation part is not there. So I is equal to Vm minus Vm by XL omega t. So it is no longer sin omega t. Also there is a negative sign, minus cos omega t. So if you simplify that, you will get I equals to Im omega t minus pi by 2, okay. I equals to Im omega t minus pi by 2, okay. Thus the current lags by voltage by an amount of pi by 2, and XL equals to omega L. This is very important. XL equals to omega L, or XL equals to 2 pi f into L. Omega equals to 2 pi f. Don't forget this as well, okay. So sometimes mainly in your PUC exam, instead of omega we will be using 2 pi f. In your KCET exam, 2 pi f can be also used, or omega can also be used, okay. But in your board exam, PUC exam, 2 pi f L is the only formula that you need to remember. In KCET exam, both formulas are important, okay. XL equals to omega L is called inductive reactance. And I equals to Im sin omega t minus pi by 2. So to rearrange this equation to this value, you get Im equals to Vm by XL, and omega t cos omega t minus cos omega t you can write as sin omega t minus pi by 2. Okay, so this is the phase difference. So phase difference here is minus pi by 2. So what is the meaning of negative pi by 2? Negative represents it is lagging. Current is lagging the voltage by pi by 2. Lagging means, suppose you and your friend are having an walking competition. Okay, you started say at 9 am, both of you started at 9 am. But what happens after some time, your friend is say 5 minutes ahead of you. Okay, so you will need 5 minutes time to catch up to him. So that is called, you are basically lagging behind your friend by 5 minutes. Okay, that is the difference. Lagging means you are falling behind, you are behind. So if you draw the phasor diagram, you will see that current is at an angle of 90 degrees with voltage, but voltage is, they are all rotating in anti-clockwise direction. Phasor always rotate in the anti-clockwise direction. Okay, so both of them are rotating in this direction, but their angle between them is always maintained at 180 degrees. Okay, so current and voltage, they always rotate like this, and they always have a 90 degree phase difference. And if this is voltage, then this will be current. Okay, current is always lagging the voltage. So in case of pure inductor, current lags behind the voltage. Very important. Average power in an inductor is 0. So if you try to find the average power consumed in an inductor, there is a way to do that, but derivation is not important. So average power spend, okay, in an inductor is 0. So even if it tries to stop the current, it does not take any power. Okay, the power it spends is 0, which is completely unlike that of a resistor. A resistor does spend a lot of power, but inductor and next in capacitor also we will see, the pure inductor and pure capacitor, they do not take any power from the circuit. So they basically just working for free. without taking any charge, right? Now, next is AC applied to a capacitor. In the same way, you can find the equation for a capacitor, which will come out to be I equals to Vm by Xc omega t. Xc equals to 1 by omega c is called capacitive reactance, same omega 2 pi f. So in your PUC, Xc equals to 1 by 2 pi f. Xc is called capacitive reactance and XL is called inductive reactance. Now if you try to write this cos omega t in terms of sin omega t, you can write sin omega t plus pi by 2. All sin tan cos, so it is positive. So you get Im sin omega t plus pi by 2. So here Im is Vm by Xc. Im is Vm by Xc. Thus current leads the voltage by pi by 2. So in this case phase is, let me check, plus pi by 2, 90 degrees. Pi by 2 means 90 degrees. So current leads the voltage by pi by 2. All of these points are very, very important for MCQ questions. Average power consumed again is 0. So average power consumed in a pure capacitor is 0. So if you see the diagram now, it is like this. So voltage and current are like this, and as they are moving in this direction, okay, current is now leading. So in the previous race you have started late, you are falling behind. Now in this next race you are driving a cycle and you are driving faster than your friend, and you have a 5-minute time advantage than your friend. Okay, so you are moving 5 minutes ahead of your friend is falling behind. So your friend is lagging, you are leading. Okay, you are leading the voltage. Sometimes I have seen, just for your information, they have asked a question. Generally whenever we say phase, it is current which is leading or lagging. Okay, for inductor current lags, for capacitor current leads, for resistor current and voltage both are in same phase. But I have seen a question where they have reversed the order and they say voltage is leading or lagging. Okay, so in case of inductor, voltage is leading. In case of capacitor, voltage is lagging. So remember that. So voltage is reverse of that of current. So there are a few instances where questions being asked that in a pure inductive circuit, voltage is leading by pi by 2, lagging by pi by 2, are in the same phase, none of the above. So voltage is in pure inductive circuit, voltage is leading by pi by 2, not lagging. So whatever is there for current, okay, voltage will be reverse of that. For example, in the racing case, you are leading means your friend is lagging. You are lagging means your friend is leading. Same case for pure inductor and pure capacitor. So keep that in your mind, okay, because this small error can make you a 1 mark mistake which can translate into a big shift in your score. Now next, RL circuit. Now we have studied L, we have studied R. Now if we combine R and L, then what will happen? Okay, that circuit is called RL circuit, and here instead of resistance, equivalent resistance, we call a new term which is called inductance. Impedance, sorry, my mistake, impedance. Okay, this is called impedance. Impedance is represented by the symbol Z. Okay, impedance is represented by the symbol Z, and it is not like simple series combination or parallel combination. It is something weird where you have to square each of the term and then add them and take a square root of that. Okay, so R square plus XL square square root. This is the impedance of the circuit. It is not simple R plus XL or R minus XL or 1 by R plus 1 by XL, not like that. It is R square plus XL square square root. Remember that. And XL equals to omega L 2 pi FL, already discussed. Im is equal to Vm by Z. So maximum current here will be given by Vm by Z, not by R, not by XL. So you have to take this Z as a resistance in an AC circuit. Impedance is also called resistance of AC circuit. Similarly, now let's discuss RC circuit. Same formula, R square instead of XL, here we have XC square, and it is given by 1 by omega C, that is 1 by 2 pi FC. Again, Im is Vm by Z. Okay, in RC circuit, resistance and capacitors both are connected like this. Next, LCR series circuit. Now you have one R one L and one C, they are all connected in series, like resistances in series. But here only one resistance is there, only one capacitance is there, only one inductor is there. So in series LCR circuit, the combined voltage across this maximum voltage Vm square can be written as resistance across the resistance square plus VL minus VC whole square. Okay, because voltages are in the opposite phase for capacitor and inductor, so you have to use VL minus VC whole square. And impedance is given by R square plus XL minus XC whole square. Now remember, in some cases you might find XC is greater, XL is smaller. Okay, we will come to those cases as well. So there you don't need to change for impedance, because XL minus XC, even if it is negative, square of that is positive, right? So you don't need to change anything when you calculate impedance. Impedance should be same formula throughout. You have to make one change, by the way, I will explain that. Current is given by Vm by Z, so same formula. Okay, so Vm by Z, calculate Z. Okay, then Vm will be given, you just need to use this formula Vm by Z to calculate the current. Phase difference between current and voltage. Phase difference between current and voltage for series LCR circuit is not 0, not pi by 2, or not minus pi by 2. It's a unique value. It can be 0 in particular case, but normally the phase difference is given by tan inverse XL minus XC, and current is given by Im sin omega t plus phi. So all this, why I am telling you this, suppose they will give you a current and they will say what is the phase difference. So from there, if the current is given, then from this phi value you can say this is the phase difference. Now XL minus XC you have to use when XL is greater than XC. So that means current is lagging. If XL is greater than XC, we say current is lagging. If XC is greater than XL, if XC is greater than XL, then you need to switch the places. You need to switch the places, or you can remember that you can use this formula, XL minus XC modulus. So no matter if it is positive or negative, you have to take the positive value. Only difference that will be happening, if XL is equals to XC, current lags, and if XC is greater than XL, current leads. We will discuss that as well, don't worry. But when using this formula XL minus XC by R, tan inverse XL minus XC by R, this is very common, and in some cases you might find the phase difference. You see, okay, XC is negative, what I have to do? Tan inverse negative value I don't remember. No need to worry about it. What you have to do, you have to take the positive value of XL and XC. Okay, so XL minus XC, positive value you take. You just remember that if XL is greater, circuit current is lagging. If XC is greater, current is leading. In a series LCR circuit, R equals to 300 ohm, L equals to 0.9 Henry, and C equals to 2 microfarad, and omega equals to 1000 radian per second. Then the impedance of the circuit is, you have to calculate the impedance. Simple impedance, simple problem. So XL equals to omega L. Omega is given 1000, L is given as 0.9 Henry, that is 900 ohm. So first step is to calculate XL and as well as XC. XC is 1 by omega C. Now if it is microfarad, micro means what? Micro means 10 to the power of minus 6, and that will be coming in the division. So I teach you a small trick that you should remember. If it is a microfarad, what you should do, you should take the 10 to the power of negative in top as a positive value. That will save you some time. Okay, be it PUC exam, be it KCET exam, if you take the micro value and put it in the numerator directly as a positive value, that will save at least 1 or 2 seconds, which you will waste in writing. So microfarad means 10 to the power of 6, which goes to the numerator directly, and omega is 1000, and capacitance is 2 microfarad, 2. Okay, so if you see that 1000 means 10 to the power of 3, 10 to the power of 3, 10 to the power of 6. That means in top you have 1000 divided by 2. right? 10 to the power of 3 means 1000. So in top we have 1000 into 1000. So 1000 is cancelled and another 1000 is left. So it will be 500 ohm. So this is how you can save time while doing calculations. Okay, so we see that impedance is given by square root of R square plus XL minus XC whole square. Okay, so only thing that I tell you is that don't be afraid to solve questions. If you are afraid, then you are dead. Jo dar gaya so mar gaya, right? You should not be afraid to solve questions. Okay, you should be bold. Jane Bold versus Jane Gold, right? The dialogue, all of you have heard it. So you are Jane Bold now, right? So 3 square plus 4 square is a very well-known number. 3 square plus 4 square is equals to 25, and square root of that is 5, right? So 3 square plus 4 square, square root is 5. So 300 square plus 400 square, square root will be simply 500. Okay, so it will be 500 ohm. Clear? So this is how you can solve some questions which might feel tricky for you. Okay, so you have to practice these questions so that you gain your confidence and start solving these kind of questions. Next, resonance in an LCR circuit. Very, very important part. Now we have seen that tan phi was equals to XL minus XC by R. Okay, tan phi was equals to XL minus XC by R. Also, the impedance was given by R square plus XL minus XC whole square. Now, what will happen if this XL and XC value they matches? What would happen if XL and XC value matches? Means they are equal to each other. So this is a unique case. Okay, and in this particular case, if you watch the resistance value, if XL equals to XC, then this term becomes 0, right? So if this term becomes 0, then the current in the circuit becomes Vm by R. So only a resistance is connected in the circuit and nothing else, as if. So this in this case the current is maximum. This current is called the maximum possible current, and the circuit will have a possible maximum current when XL equals to XC, and this particular condition is called resonance. Okay, this particular condition is called resonance. This has a lot of application. One of the very oldest application is tuning of a radio. Okay, in a radio you have a tuner. If you rotate it, it gives you the correct channel. Now most of the time nowadays we do not use radio tuners. We use our mobile phones to listen to the songs, right? And Spotify, we almost have forgotten the FM radio channels. When I was a kid, along with FM radio there was some AM radio channels was there, but then back then also it was slowly getting obsolete. But we had FM radio, and FM radio revolution happened when I was a child. A lot of private FM radio channels came, and that was our time pass. Nowadays you are spending your time in Spotify and YouTube and some other Free Fire, PUBG, etc., right? So if old radio sets if you have in your home, you should check it out. Okay, those actually worked using the principle of resonance. Okay, when the resonance is happening, each frequency has a particular resonance point. When your radio is resonating with that frequency, you are able to hear that channel. Okay, so this is the maximum current in the circuit. This condition is called resonance. If the corresponding angular frequency is omega naught, then omega naught can be calculated as 1 by square root of LC, and corresponding frequency is 1 by 2 pi square root of LC. Okay, so these are very two important concept. Okay, so you can calculate the resonance angular frequency, resonance frequency. So they will ask you calculate the resonance frequency for this given circuit. So then you have to use this formula. Okay, now in resonance, if you plot the graph of frequency versus current, you will see that normally the current was slower. Suddenly the current increases to the maximum value, then again it falls. This is the point where we say this is the resonance point. Okay, this point is this frequency is called resonance frequency. Okay, so this is the F naught. This frequency is F naught. Okay, now why resonance is happening? Let us understand that. For that we have to plot the graphs of XL and XC. So if you plot XL and XC, you will see that XL actually is a straight line graph. Why? XL equals to 2 pi F into L. So XL is directly proportional to the inductance and directly proportional to frequency. Inductance generally is constant. So if you plot XL will be a straight line. If you plot XL versus frequency, XL versus frequency will be a straight line passing through origin. In the other hand, if you plot XC, which is given by 1 by 2 pi F into C, it is an inverse relation graph. Inverse relation graph means it decreases as frequency increases. So XC is inversely proportional to frequency. So the graph of XC will decrease with time. Okay. So initially XL starts from a lower value, whereas XC starts from a higher value. So this region where XC is greater than XL, this condition gives you a capacitive circuit. So no matter if it is resistance is included or not, does not matter. So capacitive means XC has to be greater than XL. Okay, and after this point where both XL and XC are equal, okay, XC dominates, XC is, I think there is a small mistake, XL is greater than XC. XL is greater than XC. So this region is called inductive circuit because XL dominates over here. Here XC dominates, here XL dominates. Okay, so if XL is dominating, we say this is a inductive circuit. If XC dominates, we say this is a capacitive circuit. So capacitor is the more dominant one. Now at this particular point, what happens is that the XL and XC both becomes equal. So what is the circuit? This is a particular point where circuit is completely resistive. XL, XC, they cancel each other out. Okay, so so capacitive and inductive reactances are equal here. Okay, so this is the point of resonance. So XC starts from higher value, XL starts from lower value. When they meet, they say okay hi to each other. When they are saying hi to each other, they gives rise to the maximum current, and that is the resonance. So now if you plot the impedance of the circuit, that is Z. Okay, impedance means obviously Z. If you plot Z versus frequency graph, the impedance of the circuit decreases with frequency and suddenly then it goes to increase as well. So initially it starts with a high value, it goes down, and then it becomes a lowest value, then it goes to increase again. And at this point, resistance is minimum, the impedance is minimum, that is equals to R. Impedance is equals to R at the point of impedance. Okay, otherwise point of resonance. Okay, so this is the resonance condition, this is the point where resonance is happening. So at the position of resonance, resistance or impedance is minimum. Okay, impedance is minimum and XL is equals to XC. So these are the very important points that you need to remember. Now average power in an LCR circuit in general is given by Vrms into Irms into the value cos phi. Okay, here the term cos phi is called power factor. What is cos phi? So cos phi is given by R by Z. Cos phi is given by R by Z. Okay, and sin phi is given by XL minus XC divided by Z. Right? Okay, and this is called power factor. Okay, this is called power factor of the circuit. Now at resonance, what happens? The power factor becomes 1. Okay, we will discuss that. I think I should keep that formula, cos phi equals to R by Z. The resistive circuit, if the circuit contains only pure R, okay, it is called resistive. That in that case, cos phi equals to 0, cos phi equals to 1. There is maximum power dissipation. For a resistive circuit, power dissipated is maximum. Purely inductive circuit, only inductor is there, okay, cos phi is 0 and no power dissipated even though current is flowing in the circuit. This current is sometimes referred to as wattless current. Okay, purely inductive or purely capacitive, both cases, even though current is flowing in the circuit, it does not consume any power, so that's why it is called wattless. Wattless means no watt is consumed. Okay. Next is LCR series circuit. In an LCR series circuit, power dissipated is given by P is equal to V RMS I RMS cos phi, where phi is tan inverse XL minus XC by R. So phi may be non-zero in a RL or RC or RCL circuit. Even in such cases, power is dissipated only in the resistor. So L and C does not consume any power. Okay. Power dissipated at resonance in LCR circuit, at resonance XL equals to XC and phi equals to 0. So therefore power factor again becomes 1. So this is also very, very important. Power factor is 1 in resonance. So they will ask what is the power factor? What is phi? Phi at resonance is 0. Power factor is 1. Maximum value of cos phi is 1. So power factor is 1. Angle is 0. So don't confuse between angle and power factor. Angle is 0 but power factor is 1. Okay, so P is equal to I square Z, and that is the maximum power is dissipated in a circuit through R at resonance. Okay, at resonance circuit becomes purely resistive again. Okay, circuit becomes purely resistive. For a series LCR circuit at resonance, the statement which is not true, wattless current is 0, power factor is 0, peak energy stored by a capacitor equals to peak energy stored by an inductor, average power equals to apparent power, which is not true. So wattless current is 0 because current is being consumed here, does using some current and does using some power. So wattless current is 0. Power factor is not 0. Power factor is equals to 1. Okay, so remember that power factor is equals to 1. Peak energy stored in a capacitor is equals to peak energy stored in an inductor. That's why they are cancelling each other. Average power and apparent power become same because XL and XC, they are cancelling each other. So that is also true. So these statements are true. Only power factor is 0 is wrong. So correct answer is option B. Many students answered option D and they got 0 marks. Okay, if you answer power factor is 0, you would have got 1 mark, and that may cause a huge difference. Now last concept of this chapter, transformers. So for many purposes it is necessary to change or transform an alternating voltage from one to another of greater or smaller value. This is done with a device called transformers using the principle of mutual induction. Okay, so transformer works in the principle of mutual inductance. Generally we have a primary coil, we have a secondary coil. Primary, when you change the current through primary, what happens? The current, the flux linked with the secondary changes. Now in case of mutual inductance, it can be happening by changing the current manually. In case of transformers, it happens automatically because AC current changes its direction on its own, right? Every second it changes its direction 50 times. 50 Hz means it changes its direction 50 times. So when it's changing its direction, the flux which is linked to secondary changes automatically, and because of that it will also produce a current of its own, and that current we collect and we use in our household electric supply. Okay, all the household electric supply using the current that you are using at your home basically working because of the transformer. Okay, you may have heard sometimes during the rainy season particularly, transformer has busted, transformer is down, okay, transformer has burned. It used to happen a lot when I was a student, and it was a very fun time for us. When transformer gets burned, there will be no current there, so they don't need to study for a long time. Okay, so that's what used to happen in the past. Nowadays they have stabilized everything. It can happen once in, may say, 5 years or 6 years. It is still happening sometimes. Sometimes you may have heard that BISCOM has disconnected the power because there was some work going on, transformer was down or transformer is being replaced. So basically they are replacing this device. What is the role of this device? So when the current is being transferred from the power station, they are being transferred at a high voltage. Okay, and when that high voltage is being transferred, okay, this consumes a very less amount of power. Now when it reaches to your home, if the same high voltage is supplied back to you, all of your appliances will fry off. So that's why they use some stages to lower that voltage. First it is lowered from that high some kilowatt volt to 440 volt. Okay, that 440 volts is supplied to industry directly, because all industrial equipment, they are required to operate at 440 volt, and then that 440 volt is reduced again near the pole which is located near your house. Okay, generally every area has a one transformer. That transformer basically reducing that 440 volt into 220 volt, and then it is being supplied to you using various phases. There are phases of transformer. Those who will study electrical engineering in future, they will study 3 phases, 4 phases, 3 phases of a transformer. Okay, that will be complicated, slightly fry your brain, so just a fair warning. Now in a transformer, what happens is that then voltage that you supply in secondary, that you get from secondary, divided by voltage that you supply in primary, is equals to number of turns in secondary divided by number of turns in primary. Okay, so this is relation of transformer. Secondary voltage divided by primary voltage equals to secondary number of turns divided by primary number of turns. So basically the number of turns that you use in primary and secondary, that determines, so this is primary, so this is secondary, this determines how much voltage you will get. Okay, if the voltage is increasing, then it is called a step up transformer. Generally the step up transformer are used in power stations when the power is produced. Okay, and step down transformer is used to reduce the voltage which is being used in our domestic supply. Okay, even the mobile phone that you are using or the TV you are using, they also have a transformer of their own which reduces that 220 volt further down. Okay, the mobile charger generally have a small digital transformer which even reduces that voltage down to 5 volt. Okay, so otherwise your mobile phone will fry. So that's why there is a charger. Okay, you cannot directly plug a simple 2-pin charger into your mobile phone. You have to use the brick charger. That brick actually reduces the voltage. That voltage is then sufficient enough to charge your phone. The power input is equal to the power output in an ideal transformer. Okay, for your KCET level, this is sufficient. Efficiency of transformer is generally not there. Okay, so power input equals to power output. So this is the power input, this is the power output, this is power in, this is power out. So in an ideal transformer, power in is equal to always power out. Okay, so current into voltage gives you the power input, and power into current into voltage gives you the power output as well. Now generally when we are talking about I and V, it means we are talking about RMS voltages. Okay, we are talking about RMS voltages. So if I say 220 volt, that means it is the RMS value. Peak value is more than that, 311 volt. Okay, so in case of transformers, whatever value we will say, that represents the RMS value. Now formula sheet of this chapter, oh sorry, I forgot to add the formula sheet. Anyway, don't worry, I will add the formula sheet in the PDF. So if you want to download the PDF, obviously you have to join the WhatsApp channel, and whatever doubts, whatever comments that you have, please don't forget to mention in the comment section of this video. I'll be back with a new chapter very soon. Till then, bye.